Hello dear friends, I am Engineer Shah Farooq and you are watching your on YouTube channel Civil Engineer. There are different methods to design a structural member like beam, column, slab and foundation. To design a structural member, you need to follow certain design codes like British Standard Code, ACI American Concrete Institute codes, Indian Standard codes or Euro codes. Today we are going to start our discussion about flexural design of beam on the basis of most commonly used design code ACI 318. Here ACI means American Concrete Institute and 318 are collection of provisions which govern the design of reinforced cement concrete. Flexural design of beam means to design beam to resist bending moment developed due to the applied load. In design of beam means to select the cross-sectional dimension of beam and to determine the required amount of steel reinforcement to withstand the maximum bending moment developed in beam due to applied loads. In this particular video lecture, we will cover the steps to be followed for flexural design of singly reinforced rectangular beam. Singly reinforced beams are those beams in which steel design is only carried out for one side of the beam. For most cases, it is the bottom side of the beam. After watching this video full, you will get an idea about design of beam according to ACI 318 codes. In next video lecture, we will do example of flexural design of beam. So watch this video full and do not forget to like this video. Let's start today's discussion. So in this video lecture, we are going to discuss the design steps for the flexural design of beam according to ACI 318 codes. The first step is dimensions or size selection. The second step is calculation of loads. Third step is analysis. Fourth step is design, and fifth step is drafting or drawing. Now we will discuss these steps one by one. The first step is dimension or size selection. In this step we will select the cross-sectional dimension for the beam. The length of the beam will be given and we have to select the depth and breadth of the beam. According to ACI 318 codes, the minimum height or thickness of beam can be determined by using the following table. This table depends upon the support condition of the beam. If the beam is simply supported, the minimum height or thickness of beam is L by 16. And if the beam is 1 inch continuous beam, then the minimum height is L by 18.5. For both in continuous beam, it is L by 21. For cantilever beam, it is L by 8. Note that this table is only valid for grade 60 steel. Grade 60 steel is that steel in which the yield strength is equal to 60,000 psi or 60 ksi. For steel other than grade 60 steel, you have to multiply this value by this factor, which is 0.4 plus Fy divided by 1 lakh. In this step, we will try to determine the height or full depth of beam. We will also calculate the breadth of the beam. The minimum height of the beam can be calculated by using the table shown in the previous slide. Breadth of the beam is less than height of the beam. Generally, breadth of the beam is equal to height divided by 1.5. But this is just a thumb rule. It is not included in design codes. In dimension or size calculation step, we have to calculate effective depth of the beam. The effective depth of the beam is the distance from the top of the beam to the center of the tensile reinforcement which we are going to design. Effective depth of the beam is equal to total depth, which is H, minus effective cover. For effective depth, this formula is used. D is equal to depth minus clear cover minus dia of bar or stirrup minus half dia of longitudinal bar. The second step is calculation of loads. ACI 318 method is based on strength design method. In strength design method, loads are amplified or increased and strength are reduced. So we have to calculate the implied or factor load. The factor load or demand load or the amplified load can be pointed out, which is represented by demand load is equal to W is equal to 1.2 times dead load plus 1.6 times live load. This 1.2 is dead load factor and 1.6 is live load factor. The next step is analysis. So analysis of the beam is carried out for ultimate factor load including self weight of the member. As we are going to design the beam for flexural or bending moment, so we have to determine maximum bending moment value. For maximum bending moment value, you have to draw bending moment diagram for the beam. Here from bending moment diagram, you have to determine the maximum bending moment. Here this point show maximum positive bending moment and this point show maximum negative bending moment. So we have to design our beam in such a way to withstand this negative bending moment and to withstand this positive bending moment. If the beam is simply supported and it is subjected to uniformly distributed load only throughout its length, so the maximum bending moment can be determined by using this simple equation. Maximum bending moment is equal to mu, which is equal to wl square by 8. The next step and the most important step is design. Here we will use trial and success procedure for the design of the beam. In trial 1, we will assume the value of A. You can use this equation for the assumption of A. A is equal to 0.2 D. Now A is the equivalent depth or equivalent height of compression block. If we draw a stress strain diagram for the beam, so we know that the top fiber will be in compression and the bottom fiber will be in tension. To withstand tension in beam, we use steel reinforcement, while the compression in beam is carried out by the concrete. The compression stress diagram for the beam is parabolic in shape and the equivalent depth of the compression block is represented by A. So here you have to suppose A. For simplification, you can use A is equal to 0.2 D. D is the effective depth of the beam. Then find the area of steel AS by using this equation. AS is equal to mu divided by pi strength reduction factor into Fy yield strength of steel multiplied by D, which is the effective depth of beam, minus A by 2. A is the equivalent depth of the compression block. In next trial, you have to determine the value of A by using this equation. A is equal to AS Fy. AS is the area of steel in which we have determined in the previous trial. Fy is the yield strength, 0.85 is constant. Fc prime is the crushing or ultimate strength of concrete, and B is the breadth of the beam. Then you have to determine the area of steel again by using the same equation, just changing the value of A. In trial 1, we have used the value of A which we have assumed. Now in trial number 2, we will use the value of A which we have determined from this equation. Note: perform trial and success procedure until same value of AS is obtained from 2 consecutive trials. Trial and success procedure will be continued till same values is obtained from 2 consecutive trials. For flexural design of beam, generally it takes 2 to 3 trials. Now we will check for flexural strength capacity. Determine the nominal strength of the beam by using this equation. M in nominal strength of beam is equal to AS Fy into D minus A by 2. AS is the area of steel, Fy is the yield strength, D is the effective depth of beam, A is the equivalent depth of the compression block. The value of AS and A are already determined in the previous step. Design strength is equal to pi mn is equal to pi AS Fy into D minus A by 2. This pi is strength reduction factor. As we have already discussed that ACI method is based on strength design method. So in strength design method, the strength or the capacity is reduced. So this pi is the strength reduction factor. For flexural design of beam, the value of pi is 0.9. For safe design, to avoid failure, this design strength must be greater than mu, which is the bond moment, which we have already determined in the analysis step. Next, you have to check for maximum and minimum reinforcement. First, we will check for maximum reinforcement, AS maximum. You have to determine the maximum reinforcement area which you can use for the cross section of beam. AS maximum or maximum area of steel is equal to 0.85 into beta 1 into B into D multiplied by epsilon naught U divided by epsilon naught U plus epsilon naught T into FC prime divided by Fy, where beta 1 is constant and its value is 0.85 for concrete having crushing strength less than 4000 psi. B is the breadth of the beam. D is the effective depth of the beam. Epsilon naught U is the maximum allowable strain in concrete and its value is 0.003. Epsilon naught T is strain in steel and its value is 0.005. Fy is the yield strength of steel and Fc prime is the crushing or ultimate strength of concrete. You have to provide area of steel AS less than maximum area of steel to make sure that the design is ductile, not a brittle one, or to avoid a brittle design. Now we will also apply check for minimum steel reinforcement. According to ACI 318, minimum area of steel can be determined by using the following two equations. AS minimum is equal to 3 under the root FC prime divided by Fy into BD. The second equation is AS minimum is equal to 200 divided by Fy into BD. You have to select the larger value from these both values. Area of steel must be greater than AS minimum. If the area of steel is less than AS minimum or minimum steel reinforcement, you have to use this AS minimum for the design of the beam. Check for minimum and maximum steel reinforcement is carried out if the steel area is less than AS maximum steel reinforcement and greater than minimum steel reinforcement, so the design will be okay and we will perform the next step. If this condition is not satisfied, if AS is greater than AS maximum, so you have to revise your design, and if AS is less than AS minimum, you have to use the AS minimum for further design. Next, you have to find number of bars and you have to perform bar placement. The last step is drafting. In this step, based on the design of the structural member, structural drawings of the members are prepared showing the dimension of the member, which is height, breadth and length of the member, and details of reinforcing steel bars. It was all for today. Thank you very much for watching the video full. In next video, I will practically design a beam for flexural. The link of that video is available in the description box. Thank you very much for watching the video full.